So what is interesting with thermal energy harvesting is that thermal energy, the energy tank is huge. I mean, if you a change of 1 degree in a room, it's lots of joules. So we have big energy tank. But usually, the conversion efficiency is quite limited, and there is even a theoretical limit that is given by the Carnot cycle. And especially if we are dealing with small temperature variation, either in time domain or in terms of thermal gradient, this efficiency is not less than a few %. On the second source we can consider is vibrations. So vibration, they can be very nice with music and so on, but they can also be harmful, like the Tacoma Narrows Bridge, for example. But in any case, we can consider them as eligible for energy harvesting. Usually, vibration, there is a wide range of dimension we can consider. We can go from the main structure to civil infrastructures and so on. However, when we are looking at the power density, it's always in the range of a few milliwatts per cubic centimeters, and whatever the size, actually. So that means we are quite limited in terms compared to thermal energy in terms of energy tank. But usually what happens for energy harvesting is that here the available energy is less, but we can convert in a better way. So that's the big difference, to my opinion, between thermal and vibrational energy. Then we have radiations. Radiation can be either from the sun, so solar energy. Okay. By the way, the wind is a byproduct of the sun, because the sun is hitting on one side of Earth so that it makes some hot air, and then this is what creates the wind. So that's why I put wind energy with the sun. And radio frequency from telecommunications and so on. So solar energy, it's one of the premium choice. However, in some conditions, especially indoor or in environment that are confined and so on, we cannot use it at all. That leads to a big variability in terms of energy density. For wind and Friedrich, so that I explain you why I put with solar, it's strongly also related to the speed and to the density of the fluid, which can be air in the kind of wind. And at small scale, it's also quite difficult to actually use. When I say small scale, it's in centimeter scale. You can still use it in some areas, in some particular condition, but here we are speaking about small scale energy harvesting. It's not smart grid. It's not. It's really from the millimeter to the centimeter scale. And radio frequency. So typically with the main problem is that what you want with your phone is kind of sending signal, not sending energy. Okay. So here we have also very small power density. For example, antenna can usually is designed to work at few dBm, so it's much less than the milliwatts and so on, and it's very difficult to actually have significant power level. Of course, if you are very close to an antenna, or if you control your source, as Professor Mickael presented during the GNRC, controlling the source is different from energy harvesting. So if you control the source, you can apply what you want in terms of energy level, almost, not exactly, but almost, and you can play with some parameters. But if we consider true energy harvesting, so that means from something that won't be used anyway, that's something that we really don't control and so on, in this case, the source is very low. And finally, biological source. So if you take any of energy bar and you look at the nutrition fact, it's very striking. Each time I take one, shouldn't too much, but each time I take one, I'm looking at kilojoules with this size. I look at my experiment. It's 100 microwatts with the let's say, the size like this. Here I have kilojoules. I'm quite surprised, but actually there is also chemical reaction with its own efficiency and so on. So also be careful with this. Now you can see, for example, with 270 Big Macs, you can drive a car for 88 miles. So if I try to so this is, to my opinion, the 4 different sources we can consider in terms of classical energy harvesting. Again, we can discuss about others. But from what I saw, with my short experience, this is the main sources we usually encounter. If I try to compare them with several criteria, so some true scientific criteria, such as power density, but with also some criteria that cannot be well quantified, such as the flow type. Is it DC, AC? If it's not DC, is it a nice sign, or is it a big mess, like a noise and so on? Is it easy to have it at a small scale? The variability, do I have it all day, all night long, or do I have it only a particular time? And availability in general environments. So we can see here that the interesting one are the thermal gradients. Vibration are quite interesting. Solar, biological, radio frequency, as I told you, there is the issue in terms of power density, and maybe the wind. But here it's only the source. That means that's potential energy. It's not something we have at the end. We need to convert this energy. And of course, in most of the cases, we cannot convert all the energy. So analyzing only the source is not sufficient. We have also to consider the transducer itself. So how to convert this energy. So in terms of thermal energy, it's typical transduction system. We have from the thermal gradient, can use thermoelectric modules based on the Seebeck, Peltier, Thomson. These 3 effects actually almost describe the same conversion effect. So thermoelectric modules, they are pretty nice because thermal gradient is quite easy to find. They are defined by the figure of merit ZT that we will actually discuss a little bit after. But the problem with thermoelectric systems in general is that right now it's still kind of, there is, from what I saw, there is no global overview. That means you have the people from the material, they do thermoelectric modules with very high ZT. They can sell it very, with the ZT they have, they can sell it very, very expensively. But they usually, there is something missing, is actually how to interface it correctly with the environment. Because thermoelectric module, they have very high thermal conductivity. That means, and we will see an example after, that if I put it in an area, the example we'll see, I'm sorry I did it yesterday because I thought it was a good example and it's not in your handouts, but we will see, is that I have human body with a skin that might be superficially around 30 degrees. Then I have external environment at 20 degrees. So I have 10 degrees of difference that can be converted. But the problem is that with such a thermal conductivity and considering convection and superficial heat exchange, the actual temperature gradient within the thermoelectric module is very small. So be careful. ZT is not, to my opinion, ZT is not the only parameter to consider, because we need, and this is something that is more and more critical, we need to have a global overview of energy harvesting, because right now we reached a point where the progress in materials, they are outstanding. The progress in any part of energy harvesting is very important. We reach a point with very good knowledge, very good material, very good mechanical structure and so on. But now what is missing is putting everything together. Because it's not, as we will see, there is a lot of interaction between them. So actually thermoelectric modules are quite, it might be quite interesting, but be careful with the interface with the environment itself. Then we have a time domain variation, so that's poroelectric material. You had some introduction about them. So it's basically a dielectric system, and more precisely, in some cases, in most of the cases, a photoelectric material. So with a given Curie temperature and the necessity for pooling and so on. In terms of vibration, the two big families are active, so where you don't need to put any external source to make them working, external electrical source to make them working. So mainly electromagnetic and piezoelectric system. Here, usually, we use them in a dynamic way in order to let energy entering. And what is defining them the most is usually their coupling. Okay, so the coupling coefficient, Professor Mickael explained a lot about this. Just want to say there is a difference between the coupling of the material and the coupling of the structure. If you take a material that is really stiff, with a high coupling, and you want to put on a flexible substrate, the global coupling of the structure won't be good. It's better maybe to take a material that is softer, even if it has a lower coupling, because otherwise the energy will stay within the substrate without going to the active material. I mean, if you have a very stiff material, it won't have any strain. Strain will be localized in the substrate. Here it will be like clumping. While if you use a softer material, there will actually be energy entering within the material. So again, having this kind of system overview is also important to have at the end something that is globally optimized. The second aspect for vibration is passive systems that needs kind of external driving, or at least external energy sources, such as electrostatic, where we can do some electrostatic cycles, Ericsson, Stirling cycle, Olsen cycles, and so on, or electro and magnetostrictive system, where we need actually to have a bias. This is the main difference between passive and active. Here we need an electrical bias. Then, in terms of radiation, of course, from the sun, it's for solar energy, photovoltaic aspect is important. Their efficiency can be quite good, and actually the efficiency right now is higher than the theoretical efficiency, because it's a multiple junction. Here, it's the theoretical efficiency is only for a single one. So we can have quite nice efficiency, but there are still some theoretical limits. And in terms of RF energy harvesting, an antenna actually can convert almost all the energy it sees. But the problem, as we see with RF system, is that it's mostly signal, so that means there is almost no energy attached to it. It's in the order of nanowatts usually. And finally, the biological system. So it's based on chemical reaction, typically redox reaction. That makes actually something at the end that is quite low power. For example, if you want to do a nice experiment before your next Christmas, you can take your two lobsters. You put some electrodes in their brain, and you can power your wristwatch. So you see approximately the power density of the two lobsters, actually. There is also some research with rats about it, with nice pictures in the publication when you see that they opened the skull and so on. It's better not to read it before lunch. So, as previously, what I can do is to compare this conversion effect. In terms of coupling, again, we want to convert energy. So how many of this energy I can convert? How easy it is to integrate, to have it at small scale, and to integrate within a structure. Do I need a bias for it in order to work, or does it naturally by itself works? Is the electrical interface easy to do or not? And what about the interface with the structure? For example, in terms of thermal gradient, as I told you, modules that have very high thermal conductivity. That means they are kind of thermal short circuits, and it's very difficult to maintain the temperature in there. So if I compare with this different energy conversion effect, again I can consider that thermoelectric are quite interesting. Pyroelectric, the coupling is a little bit small actually. Vibration, and especially active systems, that are quite interesting. Solar is also something that can be considered. Wind coupling is a little bit small, and then we can go also to a fluidic, which is very similar to the wind. Radio frequency, very nicely coupled, but as we see, the source is very small. And biological, with here the chemical reaction doesn't ensure that there is a lot of energy that is converted. So then if I combine both of the source and the energy conversion effect in order to have an estimation of the final energy itself, with, for example, criteria that we considered previously, power density, source quality, integration, interfacing, but also, because here it's research, but it's applied research. In applied research, there is applied, so at the end we want to apply it, want to make patent money with it and so on. So also other kind of consideration about its true application. I mean, for example, energy amortization. We say, oh, energy harvesting, it's a green technology. In terms of ecology, it's very nice. If you take the solar cells, for example, or the piezoelectric element, there are some elements that are not that eco-friendly in there. For example, for solar cells, it was 10, 15 years ago, French government, they invest a lot, and they gave a lot of grants to public in order to install solar cells. But at this time, the lifespan of a solar cell, it was something like 7 or 8 years. And the time to have a positive energy balance, so that means the total amount of harvested energy bypass is bigger than the energy spent to actually make the solar cell, was 10 years. So you know there is this, what I call energy amortization, sometimes it's called gray energy, is that you are using something that is fabricated. For fabricating it, you have to spend energy. So if you want really to be eco-friendly, you have to consider this, okay? So for example, thermoelectric modules, it's a PN junction, so it's a silicon, or it depends on the application and the environment, of course. But you have also this consideration to have. So for example, solar cell, no, they are pretty nice in terms of this criteria, of this criterion. Then you have the hygiene, for example, the cost, and so on. Okay, so this is more or less arbitrary personal criteria. You have a question? No, I thought you, no, okay, no, sorry. Not now. So according to this, actually, to my opinion, you have, generally speaking, I want to insist on it, generally speaking, because this is something important, is that universal microgenerator doesn't exist. If you want to do an energy harvesting product, you first need to know your environment and your application. But if we want still to draw some general conclusion, we can say that thermal gradient vibration with active systems and solar aspects are usually the one that can be considered. But again, this is something that is tightly related to the application. And speaking about the application, here we just speak about how to harvest the energy. But once I have the energy harvested, it's not done, because we have to be also clever in the way we are using it. For example, as I said previously, now we can no longer just consider the material, then the structure, then the electrical aspect. And no, everything is tightly interconnected. The exchange are bidirectional from the source to the load through the structure and the material, through the conversion effect and so on. So now it's very important to have as much as possible this global aspect, taking into account the fact that, for example, if here scenario, the way mechanical structure is behaving. I will also modify the way the energy is entering. And sometimes, if I'm a little bit away from the optimal operating point, I can harvest more. In other words, the combination of blocks that are optimized independently, that leads to a suboptimal global system. So that's why it's very important to have some knowledge in materials, in mechanics, in thermal, in addition, in electrical, in addition to the main, to the core of your research. Okay, so that's why we provide you with this summer school. Even me, sometimes I was with quality like this. But I think that will be also the same for you with such things here. But it's very important to have an idea of what's going on out of your research scope. Something that is very important, especially for this. Also, I said how to use the energy in a clever way. Of course, if you want to sense a temperature, and you need to know whether you are in at 80 degree or in 50 degree, of course you won't use, for example, PT100 sensor with an analog to digital converter of 24 bits. If you need a resolution of 1 degree over a range of 100 degree, for example, you won't go to 0.00000 something degree in terms of acquisition, because it will waste energy without being useful. Of course, when we say this, you say, yeah, of course I will. But actually, when we see people doing it, they are not thinking about it. Okay. Another part is sensing versus actuation. Sensing and signal processing, it's signal. So that means conceptually there is no energy attached to it. And with the progress of microelectronics, we can go up to, of course, not zero energy. There will still be some losses, but and there is no energy flow. It can tend to zero. But when you are actuating, and actually RF communication is actuation somewhere, you have this energy flow. If you want to send wirelessly an information at 10 meters, and the antenna at 10 meters requires such power sensitivity, you need to send power. And in this case, you have an energy flow. You will still have losses, but I mean you have a minimum energy in actuation. So that's why I said not all the system can be self-powered. If you want to power the fan from anything, I don't know, or if you want to power any air conditioning system and so on with motors, with pumps and so on, it might be very difficult to do. So that's why correctly designing all the system is something that is mandatory. And for this, actually, the energy conversion and extraction interface is part of it. It's part of it, but it's not the only part. So that's not because we are doing electrical interface that we don't have to consider the mechanical aspect, as we will see. So let's see first how to model it. So as I told you, generally speaking, but again, it's very, very dependent on the application and environment. Thermal gradients with thermoelectric modules are quite interesting. So thermal source, vibrational source, and solar source. Here we will mainly consider two kinds of such source, so vibrational system and thermal systems. Vibrational systems with piezoelectric and electromagnetic devices, like a transducer, and thermal system with thermoelectric and pyroelectric materials. How many of you are working in piezoelectric field? How many of you have actually seen a piezoelectric element? Okay, can you tell me what kind of element you saw?
On the work itself, or?
you actually saw, you actually manipulated and so on. Cantilevers, but material. So, what kind of material? Quartz, yeah. Okay, so kind of ceramics. Okay, and in terms of systems, this is for later. If you never saw any piezoelectric element, I think it's a little bit a shame to come to see some piezoelectric energy harvesting. Electromagnetic I didn't bring. I should have bring the Indocyan one because it's quite nice, but electromagnetic, it's mainly wire. So here you have PVDF, so a polymer, okay, that is pulled by stretching. You have also copolymer that you don't need to stretch. What is interesting with PVDF? Flexibility, but the coupling is quite low. Then you have something very brittle, as you can see. So this is ceramic. So in this case, it's PZT, classical PZT. That can be, for example, sputtered on. It's quite on things like this that is closer to a structure. So this is a piezoelectric buzzer. So you have a substrate on it. Seems to be a little bit more flexible, but it's just an impression, because if you move it a little bit too much, you will hear it crunching. Another example of PVDF, if you want, this is what is called quick pack, made by Mide, but it's nothing else than actually ceramic sheet that is encapsulated within Kapton. They are selling this 90 euros. Another example I want to share with you. Another thing I want to share with you. I did my postdoc in the US in a lab that was more oriented towards mechanics. Okay, my original courses is on electronic, but I did my postdoc in a mechanical lab. And actually, they wanted to have some energy harvesting circuit and so on. And they found some company manufacturing dedicated system for energy harvesting. So they said, oh, can you have a look? Is it nice and so on? So I look at it. And for piezoelectric energy harvesting, of the dedicated energy harvesting system. This is, for those who don't know, a very simple rectifier bridge that you can find for less than €1 when you buy it a single unit. Of course, if you buy a lot of them, it will be even cheaper, with a capacitance. And you know how did they sell such a system? $100. So also, it's very important to have some, when you are doing multi-physics analysis and multi-physics systems, it's very important to know what's inside the other things. So this is a quick pack. This is something that is $90. It's really neat. It's actually quite cute. But actually, $90, the buzzer that is actually going there, it's €2, and it's performing almost better than this. And €2 on a radiosphere. So that means if you buy a lot of them, the coupling coefficient of the structure of the buzzer, I don't know where it is, it's around 20–25%, which is really high. But of course, it's not made for energy harvesting. It's made for something that is not a niche market, and so the price dropped a lot. Okay. This, what is it? MFCs for macrofiber composite. This is actually a smart device, the way it's done. Because if you have a look at it, what can you see? It's interdigitated electrodes. It allows to use the piezoelectric element in what kind of mode? Usually with bending system. How is the application? So maybe we'll skip a little bit more the electronics aspect, but I think having kind of this overview. If you want, we can go directly to electronic aspect. It's for you, the course, I mean. Okay. Here, when I'm considering a cantilever, so a bending structure, first, how should I solve? What should be the polarization of the transducer? Should be like this, like this, like this, up. So in the thickness, current direction. And how is actually here is very what's the main mechanical solicitation? Here you are considering 3-1 mode. With the interdigitated electrode, you can use the 3-3 mode, which is usually better coupled. You have higher coupling coefficient in 3-3 modes rather than 3-1 mode. Okay, so that's why the MFCs are really quite nice. They have high, quite high coupling coefficient structure, and also quite flexible as well. That in what we consider here, it's bidirectional. It's coupled system. The way I'm defining it, coupled system, is that it's bidirectional. Okay, if I apply a current to a photovoltaic cell, it won't emit some photons. Okay, but here, if I apply a voltage on my TEG, thermoelectric module, I will have temperature gradient and heat flux. If I apply a temperature gradient and a heat flux, I will have some electrical stimuli at the output. So that means I can convert either from one physical domain to the other one, but also from the other one to the first one. Okay? So what we will see also is that, as I told you, it's important to see what happens on my structure when I connect the electrical interface. So that's why it's also very important to simulate, also even with our simulation software, simulate the itself. When I say transducer, it's the structure in globality. So we'll see how to implement this. For example, how to implement the TEG, how to implement the mechanical cantilever, and so on, in a simple and simplified way in my simulating software. But be careful with this. When I'm doing equivalent electrical circuits, equivalent term can be tricky, because it's much more difficult to see what are the energy paths. We are losing the physical meaning of the system. So again, it's a very nice tool, but it's just a tool, this kind of equivalent electrical circuit. Okay, it's quite handy when we want to make simulations and so on, but it's just a tool, and try to never to lose from your sight the real system. Where is the mechanical energy, where is the thermal energy, and so on. So first, piezoelectric system. So with one of the possible constitutive equation that will link electrical displacement with electrical field, and the strain, the stress, and so on. How to go from a microscopic point of view. There are several ways to do it, more or less complicated, whether we are considering longitudinal excitation, bending excitation, and so on. But basically, the electrical displacement. What's the unit of the electrical displacement? D. Or if you prefer electric induction. Coulomb per square meter. Okay, so Coulomb, it's charge. So it's when we are going from the local to the macroscopic aspect, it will be linked to a charge. Usually in electronics, we are not considering charge itself, we are considering its derivative, that is the current. Electric field, the unit. Should have made a poll with this. What is the unit? Volt per meter. So when I'm going from local to macroscopic, so I'm integrating over the dimensions, it becomes voltage. Stress, What's the unit? It's homogeneous to a pressure, okay? And when I'm integrating over the surface, I have a force. Strain, what's the unit? But usually we like to consider meter per meter, micrometer per meter. That leads to the definition of micro deformation. That is micrometer per meter. Of course, it has no unit, but at least saying it's micrometers per meter or meter per meter help in reminding it's a mechanical quantity. So if I integrate, I have a displacement, and then I have so this is the quantity, and then I have the parameters. Of course, the permittivity, when I do the integration over the space, it's a dielectric, so I have a capacitance. The strain, the compliance, and so on with the Hooke law, when I will do integration, I have a stiffness and so on. Then I apply the fundamental principle of dynamics, and what I have is from this one that is a local constitution to this one that is a global system. And this one is local and material aspect. Here there are several kinds of materials, the substrate, the transducer itself, and I have something that can be seen from the mechanical point of view as spring mass damper system with a coupling in terms of voltage to force, so a coupling in terms of the excitation, and on the electrical aspect by a current source that is controlled by the velocity, and also, I should have added here, with capacitive internal impedance. Okay? So this is for piezoelectric elements, so there are some mechanical aspects, quite difficult to implement within electrical software. So how to go from mechanical to electrical? So I have my spring mass damper system. I want to go to the electrical aspect. So what can you say me about mass? When I say mass in mass. It's obstacle. Yeah, of course, if I'm moving my remote to you, it will be either the remote or the, yeah, thank you, or you will be the obstacle according to the reference. But mass moving. Inertia, okay, yeah. What is related to inertia? Yeah, okay. If I'm just dropping my to you can take, okay? But if I'm making the velocity much higher, it can be a little bit, it can be hurtful. Why it's hurtful? Because you have to dissipate more energy. So mass, it's related to energy, and what kind of energy? Kinetic energy, because it's a movement. Potential. I mean, point of view from the system level point of view. What is the potential energy? What is it? Okay, do you have your elastic with you? Why I say it's potential energy?
You can use my hair.
No, you don't have it. Ah, Osrine, t'as pas un élastique avec toi? Oh, ah, okay. If I take something for the hair, just to hang them with the elastic. If I take the elastic like this, and I release it, you will feel the elastic energy, the potential energy. It's still potential because there is no movement. Yeah, exactly. So that's why here you have kinetic energy term, potential energy term. And the damper, it's in terms of energy, movement. So you see we have this kind of equivalent between mass, inductance, spring capacitance, and damper and resistance, because resistance, Joule effect, and so on. It's even more striking when I write the equations, almost the same equation. Okay? So we see the mass, inductance, damper, resistance. One small difference, it's here, stiffness, inverse of capacitance. Sorry, there is a zero missing here. Inverse capacitance. And we can see also displacement, charge. So that's why I was also speaking about the current, that is the velocity of charge, because when we have the velocity, we have the current, okay? And force, and here, voltage. And this is what I said also, in terms of energy, we can also find this equivalence. So that means this, I can totally represent like this by matching the mass with the inductance, the damper with the resistance, the stiffness with the inverse capacitance, and then I consider that when I apply a force, here I put a voltage source, and my current is actually the velocity, or the displacement is given by the charge on the capacitance. Okay? So this is exactly what I explained. So we can actually transform this mechanical equation into an electrical one in order to simulate it. Okay? However, here it's a coupled system, what we saw previously. And what we saw here is just a simple mechanical system. What is the coupling element? Actually, what we can do, and it's a Mason modeling, is that the energy conversion in terms of electrical aspect, it's a transformer. And we can use this transformer actually here in order to show in a purely electrical domain the coupling between the mechanical branch and the electrical one. And like this, you have something that is totally equivalent to this. Okay? If the coupling is low, so that means if I change my electrical conditions, I won't change a lot my mechanical response. I can just get rid of the mechanical part and just consider here that the displacement is only fixed by the mechanical excitation. Okay? What we saw quickly for this, what we saw here, the spring is efficient to have an idea of the behavior close to 1 resonance. And here we have only 1 piezo. If I want to extend several resonances, bending mode with maybe and so on. If I put several piezoelectric elements, okay, to have kind of distributed system, manage it in there. Actually, several piezoelectric elements, in terms of the force is adding. So for a given mode, I put my transformers in parallel. Okay. The principle of taking into account several modes, the hypothesis is that there is no crosstalk between the modes. The modes are independent. Okay. So I have my mechanical branch that are totally independent, but they have the same force. So that means they have the same voltage. So they are all in parallel. Okay. And finally, for one piezoelectric element, I have the summation of the contribution of each mode. So that means I have the current source that are in parallel. So the transformer here that are in parallel. Okay. Of course, I can also present this as a matrix form. So for each mode, I have one line of the matrix. And at the end, in order to have the total displacement, I just do the summation of each each displacement corresponding to each mode. Okay, so we can either implement numerically with MATLAB, for example, or by hand, things like this, or to directly implement in the simulating software.